Okay, hello, and this is the case study um, review by Ali, Raphael, Charles, and awjad. It's to do with the improvement of optical ground wire resistance against lightning. So I'll just briefly go through the introduction. The case study is based on another study by Sia Karabey, Ersin Asim, Alpay Tamir at the Mechanical Engineering Department of Kocaeli University, Turkey. So we've provided the relevant tables and images from the original case study so that we can directly reference and back up what we're discussing. The briefly it is about an analysis of the enhancements of alloys of transmission lines over traditional transmission lines to make them more resistant to lightning and to make them more conductive so that there's less resistance, of course. And to also withstand higher temperatures, higher tension, and flashover, which is a phenomenon that I'm going to go through later. Okay, so this is just the main part of the case study. Overhead transmission lines are designed to transmit electrical power from one place to another for consumption. Lightning may induce electrical arcs. Now, one of these problems, as I mentioned before, is flashover. This is a phenomena whereby voltage causes electrical energy to pass through insulators, therefore breaking them. Flashovers are dangerous to people operating around, and has been known to cause death and other damages, and is very costly, of course. Lightning intensity differs from time to time and from place to place, and in different environments, of course. So the wires that were designed had to withstand different temperatures, different amps, different environmental conditions, of course. So it could be in winter conditions or indeed in tropical conditions where there's a high amount of lightning strikes. Okay, so let's just move on. Here's a photograph of traditional transmission line after arcing from lightning. Right. Okay, so the theory. This is the main part that was done by Raphael and I. The case was to analyze modifications of the alloys that are composed of the OPGWs. At first, the idea was increasing the melting point of the alloy and then drawing it out. But the presence of impurities in this material also increased resistance. I'm not going to go too more in depth about this, but zinc and titanium can also be in the melting pot at the time of creating this drawing out of the wire. So the conductivity of the material depends in the material, the temperature, the impurities in solid form. So we just gave a formula there for that. The thermal constant is related to the vibration of the atoms that compose the material in crystal lattice forms. So basically creating the wires itself, creating the molten metal for it is incredibly difficult, and also it slows down the process because of it. Okay. Yeah, as I said before, the impurities such as titanium, vanadium, chromium, zirconium. Sorry. Okay, and during the metal process, an alloy of 3 kilos of AlB2 was added per ton of the original aluminum, magnesium, and silicon alloy, increasing its conductivity and making it resistant to high current levels that would cause breakage. It's also important to note that the main mechanical characteristics of the material were considered before and after modification. Breaking low, tensile strength, as mentioned before. Elongation was assumed constant after the inoculation with AlB2, and the material all mechanical and electrical requirements. So this is just a table after the short circuit test and lightning test were performed. So the significance of failure prevention, as outlined in the previous section, the two most significant consequences of lightning strikes on transmission lines are flashovers and induced over voltages. Of course, these are known to damage electrical circuits, power supply, and they're costly. Okay. And yeah, this phenomenon can be controlled by designing better insulators, overhead ground wires, which are mentioned in the case study. Okay, so that's about it. Thanks.